Today we're talking about calculating potential energy. And one of our main focuses here in our chapter 5 is going to be talking about our gravitational potential energy and also, to a lesser extent, our elastic potential energy. So let's talk about gravitational potential energy. By and large, when we say, hey, what's the potential energy of this object, we're probably talking about gravitational. So how do you calculate it? Well, potential energy gravitational equals m times g times h, the mass of the object times the acceleration of gravity times your height above zero. And the cool thing about this is when you discuss this whole height above zero situation, that is somewhat a flexible idea because you can define where zero lies. In most of the case, we consider the ground to be zero. But think about the pool for a second. When you stand on the diving board and you're, for say, 5 meters above the water, you're probably going to consider the water to be zero. But here's the thing, once you hit the water, unless it's frozen, you're going to keep going. And therefore, you could be below zero with gravitational potential energy. Therefore, you could have a negative gravitational potential energy. It's just something to think about. The idea of zero is somewhat flexible, and that's just something to think about. Okay? So mgh, it's a very simple calculation. So if we were just going to use my little example here of 100 kilograms times 5 meters times g, 100 times g would be 981 times 5. That would give us 4,950. I think I did that in my head. But that's just all you do. M times g times h. Very simple. Then we talk about elastic potential energy. A little more complicated. You have to kind of think back and remember back to when we discussed Hooke's law last chapter, and we talked about how Hooke's law was F equals kx, and we introduced how k was the spring constant and x is the displacement of your spring. Well, k and x are back, and they are the same thing still. So k is your spring constant also still today, and x is your displacement. The difference is you take 1/2 of k and you're doing x squared. Just the x is squared. So k is your spring constant, x is your stretch of compression. So now we have Bob bungee jumping above the pool, and if the spring constant of his bungee cord is 50 newtons per meter, and he is stretching it out by 3 meters, we would say 1/2 of 50, so 25, times x squared, so 25 times 3 squared. Well, that'd be 9. 9 times 25 is 225 joules. And that's just all you do with it. How much you stretching it out. That's your x. So a little sample practice here. Bob is on top of a bridge, then Bob jumps off the bridge. Bob has a bungee cord that has a relaxed length of 15 meters and it has a stretched out length of 44 meters. We would like to know, what is Bob's total potential energy? So we need to go in chunks here. We got to do elastic potential energy first. And so when I'm looking at it, when I want to do, let's see, 1/2 of k, 1/2 times k. K is given in the problem here. 71.8 newtons per meter. Sorry, I'm going quick. Times x squared. Now, here's the trick. We have to look at those numbers and say, what's my x? If my bungee cord was 15 and now my bungee cord is 44, I need to subtract and find the difference between these two to see how much it's stretched out. So 44 minus the 15, that comes out to 29. So times 29 meters, square this thing, square that. And so this is just calculator work at this point. So 29 squared, that's 841 times 71.8. Okay, and then I got to take half of it, so divided by 2. So I got 30,191 right there. 30,191 joules. Oh, 0.9 joules. Okay, so that's my elastic potential energy. Then for my gravitational potential energy, mgh. So part of that's real easy. M is 70 kilograms times g, whoops, times 9.81 meters per second, that is squared, times h. Now, this is the tricky thing. When we're solving the problem, Bob is not standing on top of the bridge. Bob is here. And if we're saying that the bungee cord stretched out 44 meters, what height are we going to be using for Bob, given that it was a 50-meter bridge? We're going to use this here, this 6 meters that's down here. That's the height we're going to use because he is 6 meters above the water currently. So now I got some more numbers. Let's go 70 times 9.81 times 6, and I get 4120. I get 4120 joules. And then the question says, what is the total potential energy? And so I just add these up. Plus 30,192 comes out to 34,312. And with that, I think, do I tell you where the problems are on the next page? There we go. 166 is the homework to do here. 1 through 3 and 3 and 4. So there's 2 little question sections to be answering.